Hello and good morning. Welcome to this presentation about how to find your next deposit using lineament analysis. My name is Ricardo Valls. I'm a graduate from Moscow Geological Institute since 1983. I'm also a PGO registered in the province of Ontario and a qualified person. I am also the author of several books on the subject of geology, QA/QC, and the use of machine learning and artificial intelligence, mainly to process geochemical data, but geological data in general. You can obtain a copy of this presentation just by emailing me at valsvg@gmail.com, so there is no need for taking notes. The presentations also include some sources and videos. To the left here you have a video from my colleague Dr. Vadim Galkin. He explains in detail all the theory behind the lineament analysis. To the right is a little history of the work that we have done using lineament analysis. The process of discovery of a deposit is a very long one. So companies usually try to figure out ways of cutting the time. Normally you get to study data in a library, then you need to do the geological mapping, satellite interpretation, geochemical sampling, geophysical sampling, and at the end, drilling, which is one of the most expensive ones. One way some companies try to cut costs is to guess and to try to grab the cat by the tail. Usually Mother Nature will punish you for doing that. Let me tell you about a real case in Colombia. There was a company A that has a license and they did all the required work, mapping, geochemical data, geophysical interpretation. Finally, they find a zone, they drill it, and they find out a good ore zone. Next, a company that was located, that acquired license next to them, realized that, well, we can save all that. We know where the mineralization is coming from. So without any work, any geological or chemical sampling, they just start drilling, hoping that they will intersect the same mineralized zone that was detected by the other company. The reality was that between these two licenses, right at the border, there was a fault. And of course, the mineralized zone has shifted north. So all these holes done by this company were for nothing. They didn't intersect any mineralization at all. We have tested this method since 1999 in different types of deposits, metals, oil and gas, nickel laterites, and more recently in gemstones, emeralds and rubies, which is very interesting. So how does this work? First, we start with the selection of the area for the lineament analysis. Then we do a three-dimensional modeling and rows diagrams. Then we do the data processing and finally the graphical representation. Well, we have done more detailed lineament analysis on small areas less than 25 square kilometers. Usually the method works better when you have larger areas. 50, 100 square kilometers will be the minimum. One of the reasons is because a circular structure in a small area could look like a lineament, like a main lineament. So that will generate problems during the interpretation. The other thing is that you need to select an area, especially if you're doing three-dimensional modeling. You need to select an area that is larger than your current area of interest to avoid the deformation effect that gets around the borders of your area. Here we will be talking about 4 lineaments. Main lineaments, which are linear structures of more than 10 kilometers in length, secondary between 1 and 5, tertiary less than 1, and circular structures. If you want to do a little practice, please print this map out and we will draw some lineaments on it. You can start by drawing main lineaments that you can see here. So I will just look for structures that are in a line, in a direction. As an example, I have drawn here 5 lineament analyses. They are not all that they are, but just some examples of the most important main lineaments that you will find in this thing. Now try to find secondary ones. Again, I'm just showing here some examples of secondary ones. In the next step, we will try to find some circulars. As you can see, there is a couple of good circular structures here. So the next step is to combine all these lineaments and to identify the points of intersections between them, between main and main, between main and secondary, secondary and tertiary, circular and secondary, all points of intersections. So the final step will be counting these lineaments. For that, we start by overlaying over this map a grid that could be 1 square kilometer or 500 by 500. It depends on the degree of detail that your client wants this work to be done. And of each square, you count how many main lineaments, secondary, tertiary, circular structures are, and the amount of intersection between them. Just as an explanation, I have included here 2 examples of this, of how we count. And I will tell you that at the beginning, we have now a software that does this for us, but at the beginning, for many years, we did this by hand. So it is possible to do, it just takes a longer time. Three-dimensional modeling include plastic and elastic deformation. A plastic model, we create a model with mud and sand, and on that model we trace the main lineaments. And then we subject this model to the different type of deformation, which are shown there with the different red arrows. And what is very interesting is that no matter from where the pressure is coming or the extension is coming, there will always be a group of folds that will open, and there will always be a group of folds that will close. Each experiment is repeated 2 or 3 times. Each result is photographed, and because we are looking for those places that will remain open for the most part of the time. At your left, you see the result of the experiment. In red are those places that remain open for most of the modeling. In blue, the ones that remain closed for more of the modeling. And why is this so important? Because really, geologists should be looking for spaces, for volume. It doesn't matter, you may have the most beautiful geochemical anomaly on surface, and it may be the result of a grain of gold that happened to fall in your sample. What you really need to find are spaces where a deposit could form. I use the analogy of a geologist is a person that goes into a kitchen trying to find a pan, a big pan, and the lights are off. So you have the option of going systematically, step by step with a match, trying to figure out where this pot is, or just go around and hoping to get lucky and find the pot. This method will tell you where the big pots are in your target. It doesn't tell you what is inside the pot. That will be done with your chemical analysis and your physical, etc. But for at least it will allow you to reduce your area of exploration to those parts that really have the possibility of containing a deposit. The elastic modeling is faster. Instead of using a model made of mud and sand that every time you deform get destroyed and you need to redo it again, for the elastic modeling we use gelatin, where we mark the main structure. We use a polarized paper from below and a source of light, and when we do the deformations, you get the spectral the spectral deformation of the light, red being the more intense openings, blue being the more close environments. So it's the same method. We are looking for areas that will remain open most of the time, no matter from where the deformation came. Of course, if you are working in an area that you know for a fact that the area was subjected to a lateral compression, then you don't need to do all the models. You just model the ones that you know that works in your area of exploration. And then we use different softwares to represent these anomalies. And of course, the target will be that place where both the elastic and the plastic deformations indicate the higher values of deformation. This is your target. We have done this so many times, and I believe that the time that we were able to reduce the area for the lease was 50%. Usually we reduce the area by 60, 70%, even before you start working in your project. This is the type of study that you do before you put a foot in the ground. So it really allows you to concentrate your exploration dollars on the best targets, on the target that have the possibility of containing a deposit in a volume, in a space below the ground. The next step will be to add all other source of information that you may have. I must say that this technique will work just on the basis of a digital elevation model or a topo map, but it works much better when we can add layers of geology, geophysics, geochemistry, etc. The more information, the better. It is important that the areas that the type of data that you want to add are completely enclosed within the area of your study. You cannot use, for example, a geochemical data set that doesn't cover the whole area. This is a little trick that I use when I need to work with maps, hard copies that are not digitized, and it takes time to digitize a complex map like this. So it's very simple. You just open your data with Adobe Photoshop or GIMP2, find the eyedrop util, and you just put the eyedrop on top of your image following a grid, and right here down at your right, you will get the composition of that area, which I usually put 3 by 3 pixels to cover a larger area as an average, and then I move it up, 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 and you will get a digital representation of your pixels. To do this integration, we use correlation analysis that allowed us to integrate all these different sources of information. The difference between our method and the hyperspectral method that you see here to the right, usually the hyperspectral method, they will have like 500 layers, and they say layer 30, 45, and 170. When you put them together, that will be montmorillonite. And those other three, that will mean quartz. Our method creates just one layer of information, a map that we call the prospective map. Another source of data is ROS diagrams, and this is something that can be done and usually done directly in the field, but how the problem was how to get that data into our system. And I created the flow chart that you will see here to your right that allows you to interpret each ROS diagram as a geometrical figure, and each geometrical figure has a value, so you get digital data that you can integrate and do correlation analysis and all the fact that we do with our analysis. Once you have all your data, you will get a table in Excel that will go from here to the next wall. It's usually very, very long. You have here the columns UTMs, east, north, main, secondary, tertiary, all amount of intersection between main and second, main and tertiary, etc., 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 plus all the geophysical, geochemical, geological, Rose diagram data. So it really becomes a very, very large data set. After that, you start doing normal mathematical modeling, like determining the distribution law, eliminating hurricane or outlier, statistical outliers or hurricane values, and to prepare your data to do correlation analysis. And the correlation analysis allows you to create the figure that you will see here to the right, which is called a dendrogram, that represents the relationship between the different units the parameters that we are measuring. I forgot to say that once you have this data, the method works much better when you have within your target a known area of mineralization. In that case, if you have an area that you know that there is a type of mineralization that you're looking for there, you divide your data set in two. One that covers this mineralized area and one that covers an area that you know for a fact that is barren. And the objective is to get this coefficient, correlation coefficient, which I call the RCC, and that will be different for the mineralized zone than from the barren zone. So again, you will have the same amount, the same types of lineaments, no matter where, on top of the deposit or in the barren zone, but the relationship between these lineaments will be different, and that is what's going to help you map define your nets or body. Another method that is very useful is factor analysis. The only problem with factor analysis is that it's a mathematical tool that is very difficult to understand the geological meaning. So it's almost a try and test and see what you get and see if you can interpret it. But because it's a mathematical method, it has also the advantage that it's unbiased. So just use it also. As I mentioned before, instead of having 15 or 20 or 30 maps, even if you do additive anomalies, etc., you will get a lot of different maps. Here, with our method, you get one single map, which we call the prospective map. And that prospective map can usually be simplified just to determine the target's area. This is an example in Armenia, where the client had an area originally of over 500 square kilometers. We reduced that area to 4 main targets. So by 75%, we reduced the area. And all the work that have been done, exploration work that have been done in this area has been very, very successful. For most of our graphical representation, we use Surfer, but there are many other software available to do that. But the thing is, you can represent target areas here. To the right is a graphical representation of the Rose diagram. This is a real case study in Colombia in the area of Remedios from a company that have several mines in the area, which correspond to the, let me see if I can use this thing here. All the deposits are in this area here, and we found this new target zone for them, and they are currently exploring it. So here is a little bit of information about us. As I said, my name is Ricardo Valls. And for my good friend and colleague, Dr. Vadim Galkin, who is the brains behind this method. As I promised at the beginning, these are other sources that you can check to see, to learn a little bit more about the method. There are several companies that have filed their 43101's report on CEDAR, so they are public information, and you can find results of this method there too. You can contact us here at Financial Consulting Toronto. And again, thank you very much for your attention, and we hope this presentation will help you find your next ore deposit or oil and gas. Have a good day. Bye.